Okay, so back to the meta tutorial so that I get through this. There was I was I'm still at in the introduction. Damn. All right. Okay. Uh, so I was just generating a random binary list in the last video. I was also generating a random binary tree and so forth. Now, solving problems with recursive nondeterminism. Now let's try to solve some problems using this. All right, so I'm gonna type this again. Bin 0 and then bin 1, so it's both. Then gen a binary list. Okay, what do they do? Then sum the products of elements of two lists. Candidate solution. What? Let us put. So maybe I should read this. Read the text. Let us put all the pieces together and solve the subset sum problem. In this problem, a list of integers is given, and one needs to find its elements whose sum will be equal to a given target sum. Yeah, okay, so kind of like which subset is the subset where you get this a specific sum. Yeah, so that would be an obvious candidate problem to solve with this combinatorial non-deterministic evaluation that we had. So we can list all target solutions with this gen. This will make all the binary lists. Here you say the scalar product, okay, and then we find from all the solutions we find the one. So let's see how to do that in Meta. Candidate solutions in this problem can be represented as binary lists. Then the sum of taken elements can be calculated as the sum of products of the elements of two lists. The elements are wait, a list of integers is given. Something like 8, 3, 10, 17. Say that you want to find the subset where this is exactly 20, or you find all the subsets where this is 20, I suppose. So we immediately see that this must somehow return a list with 3 and 17, right? Yeah, but you can represent the candidate solutions as binary lists. Okay, I think I know what they are going for. So that you have basically a mask, a list mask, like 0, 1, 0, 1. So you say that I skip the 8, I take the 3, I skip the 10, I take the 17, and then I take the product. Yes, then I take the product. I get it. I know. Now I see. So if I take the product of my mask times an input, this is basically saying it's the same as saying this is a subset of the input, where the complete subset would be everything 1, and the empty subset or the empty set would be everything 0. Then this should say 0 here at the end, or the outcome of that should be 0. Yeah, okay, let's type this in. So I get the structure of the problem and the solution, I think. So first, define a function called gen binary list. Okay, that with the pattern empty list is nothing, and then gen bin list with the pattern of a list. Okay, with a pattern of a list says a new list with bin and gen bin list. Yeah, we already did this one. Yeah, with the rest of the list. Yeah. Then sum of products of elements of two lists. Yeah, this is called scalar product. So with empty list, you get 0. Then we say scalar product with a list $x and $xs and a second list. That would be $y, $ys. Now we say plus the first two elements y and y, x and y, and then the rest recursively scalar product with the rests like that. So now you could take scalar product of 0 and 10 or something, and that should be 0. Evaluate this, I mean, yeah, should be 0, and if I have a 1 here, should be 10, right? Yeah, okay. Yeah, and now something cool. If I say 10 is my input, and I say this, give me the gen binary list of this 10. Now I get both 0 and 10, and that's the cool thing. So sort of from this logic, we are building up now the solution. Okay, so check candidate solution. I'm typing what they say. Test solution. Oh, this is already it. Okay, so numbers is the list of input numbers. Solution is sort of the target. Oh no wait, solution is. How does that work? Okay, yeah. The solution is the binary. Is this binary this mask, and then target sum. Okay, that would be the target sum. If the equal the scalar product numbers solution are okay. Return the target sum. No wait, if this is equal to the target sum, yeah, then return the solution. Oh well, I mean, yeah, that's the solution. Else empty. Okay. Else empty, so that I don't clutter everything with sort of solutions that are not actually solutions, I suppose, or something like that. And this is the solution to the problem. This is really cool. Okay, I'm gonna copy this. So that would be the task, and we said that the outcome should be 0, 1, 0, 1, right? As sort of solution mask, sub mask. So now we evaluate the test solution, and we say that there's a task. Then we say that the solutions, all possible solutions, kind of gen binary list from the task. And we say the target is 20. Okay, so that if I evaluate, this takes quite a bit. What the hell? Okay, not sure where the bottlenecks are, but yeah, I get 0, 1, 0, 1. But yeah, this is really cool. That the solution would be on this high level. Yeah, and this is of course, yeah, if you think in a relational programming, we say, yeah, for all the solutions, kind of like look at all the possible solutions, and then if the scalar product is the target sum, so then this is what the solutions, this is what we evaluate to, what we reduce to. Yeah, so you get this concept of sort of saying the shape of the target, saying the relationships, instead of some kind of procedural thing where we would go through the solutions or something like that. And this gen binary list has a lot of does a lot of work, because it's already it's representing all possible binary masks of a list that has the shape of this task. Naja, either way. Yeah, so it's kind of cool. Okay. Okay, I'm not smart enough right now to understand the difference with the frog example. I just keep going to the next tutorial. Meta from the ground are patterns of knowledge. All right. Maybe I give it a new name. I give it the name patterns.meta. Okay. Text scale increase repeat. All right. Querying space content functions and unification, nested queries and recursive graph traversal. Okay, let's go through this. Querying space content. As a declarative language, Meta was designed for expressing complex relationships between entities of various types, performing computations on these relationships and manipulating their structures. It allows for programmers to specify AI algorithms, and I'm trying to bring in a little bit of German accent. This is kind of like my style, my spiel. So basically, I'm trying to find a groove where I can bring out the most German accent that sort of makes sense to me. That's the sort of like in a space of not being cringe or something like that. No, let's see. It allows programmers to specify AI algorithms and knowledge representations in a rich and flexible way. Metacode can be generated and processed in runtime by meta programs themselves, which adds a lot of dynamism in working with complex data structures for AI tasks. Yeah, so you want to take metacode, do something with metacode, but we also say we talk about the relationships, and I guess the cool thing would be that we talk about the relationships of code or something like that. Now let's see. One of the main purposes of developing Meta was to operate over a knowledge metagraph called atom space, or just space, capital letters, designed to store all sorts of knowledge from raw sensory motor data. So there's probably sort of a stream of high dimensional inputs or something like that, or some kind of input streams, bit streams, to linguistic and cultural knowledge. That's probably more something like an RDF database. To abstract mathematical, scientific, or programming knowledge. That's probably more something like functions and expressions and relationships or something. Atom space represents knowledge in the form of atoms, the fundamental building block of all the data. Specifically, in the context of AI, an atom can represent anything from objects to concepts to processes or relationships to reasoning rules and algorithms. Yeah, so the atoms are supposed to glue everything together, and then we have this relational programming language to put this together or something like that. Let's see. While Meta may look like an ordinary language in certain aspects, it is built on top of operations over the knowledge metagraph, which is essential to understand how it works. Okay, let's get into the knowledge metagraph, I suppose. Knowledge declaration and matching query. All right. Let us look at the basic example of specifying relationships between concepts, e.g., family relationships. While there are different ways to do this in Meta, one can simply put expressions like the following into the program. Yes, so we say parent, Tom, Bob, and that's already something in the meta expression space. This expression being put into the program space can be treated as the fact that Tom is Bob's parent. Sure. Yeah, by convention, I suppose, kind of. So, relationship. It's almost like RDF. There would be attribute, entity, attribute, value. Naja, okay, it's not. No, it's not like RDF. Here we say the relationship, and then we say that Tom is Bob's parent, for example. Okay, so it's like relationship, object, subject, or something like that. Subject, object, something like that. I think Tom is Bob's parent or something. No, either way. We start parent with capital P to distinguish it from a function. Okay, cool. So relationships have capital letters and functions have lowercase letters, which we would prefer to start with lowercase p in this case, although its naming convention is not mandatory. One can add more such expressions to the program space. But what can we do with such expressions? The tutorial overviewed the evaluation process of expressions for which equalities are specified. But is there any use of expressions without equalities? Aha. Aha. Let's see. The core operation in Metta is matching. It searches for all declared atoms corresponding to the given pattern and produces the output pattern. The process is similar to the manner in which we can search text strings with regular expressions. Yeah, so you put a star, you put a number, like you say this to say match all the numbers, like something like that, and then something else you say this to say match a single white space character, and then this to say match anything. So, but now we have this kind of programming paradigm, but instead of strings, we have these expressions, suppose, so that we can say something like $X, and it means all possible relationships between Bob. Actually, this returns something, no? This returns something. No, it doesn't. I would have thought this returns parent, no? I thought this returns parent Tom Bob, no, or something. No. I guess I need to match. I guess I would need to match. Okay, let's continue in the text. The process is similar to the manner in which one can search text strings with regular expressions, but now we are doing this with subgraphs in a metagraph. We can compose a query for matching using the grounded function match. It expects 3 arguments. Okay, match. I'm just gonna, match. I'm gonna go through the basic example in a sec. Okay, first we need a grounded atom referencing a space. Then we need a pattern atom to be matched. This needs to be some kind of pattern. Okay, and an output pattern typically containing variables from the input pattern. Okay, so I think, yeah. So the space you say ampersand self to say the space in the program, or the current program space. And now I think I can do what I was just thinking, something like Tom Bob, and then just $X. Shouldn't this be like all relationships between Tom and Bob? Parent, yeah. It's 2 times because I evaluated this 2 times. Okay, something like that. Let's go into the examples. Let us consider the following program. Okay, I typed this in. Parent Bob Ann. All right. This match will be successful. Okay, evaluate. It's a little bit big. Where am I? Here. Okay, match ampersand self, parent, Bob, and okay, this is boring, right? Bob is Anne's backroad. Anne's father. This will say Bob is Anne's father because we match this one-to-one in the atom space now, right? Now I get it twice. Yeah, okay. That was basically obvious, or yeah, that was the basic case where this matched with the current atom space. Okay, so now I say Joe here. Bob is Joe's father, and this nothing. Okay, nothing, because parent Bob Joe is not matched in the atom space. Okay. Ampersand self is a reference to the current program space. We can refer to other atom spaces, but we will cover it later. The second argument in the first match expression, parent Bob N, is an expression to be matched. The second argument in the first match expression, so this parent Bob N, is the expression, the pattern or expression that we match with the atom space. And the third argument is sort of the outcome. What will be returned? Okay. The program above, first it returns that Bob is father, and here it returns nothing. Since when the desired expression pattern wasn't found, match returns nothing. Yeah, so we asked the program, does this pattern match anything? If it matches anything, then return this part. We can construct more interesting queries using variables. Okay, let's put this into a database, into the program. Maybe make more space. Okay. Yeah, like this. So all these relationships. Now I say match ampersand the self, the current program space, parent, anybody, $X, anybody that I call X, I suppose, Bob, and then return X. So this asks who's Bob's parent, and because I have put this multiple times into the atom space, I get this multiple times. But yeah, Bob, yeah. So we can also ask Liz, and here I only get Tom, and okay. So if I ask for Bob, I get this list, and if I ask for Liz, I get Bob. Yeah, because I asked for all the parents of Liz basically. Okay. The pattern parent $X Bob. Who are Bob's parents? Can be measured against two atoms in the space, and the corresponding bindings for X will be used to produce the result of match Tom and Pam. Here we will get Tom and Pam, which can be viewed as non-deterministic evaluation of match, so multiple results. Please note that match doesn't search in sub-expressions. The following code will return an only. Okay, if I type parent Bob N, I already have typed this, so I'm not gonna evaluate it again. Then I say parent Pam, and now a sub-expression. The parent of Pam is a parent of an entity that is well, it's actually this relationship between Bob and Pat. I'm not, yeah, it's already a bit strange to even try to express this in terms of words, I feel like. So if I say no parent Bob, x, so it returns an, but it doesn't return pad. So it's like, even though this expression is in the atom space, this parent Pam, parent Bob, pad, this one is in the atom space. If I ask match with the atom space for what you might think it might return pad now, because isn't this in the atom space? But it's not the case. It doesn't look into its sub-expressions. It only looks at its top expressions, I suppose. Consequently. Okay, so that's just for info. It doesn't look into the sub-expressions. Yes. Yeah, that was important to know, I suppose. We can make even broader queries. Who's the parent of whom? Yeah. I already did this once, yeah. So I can. That was. Yeah, so you say match ampersand self parent x and then $y. Yeah. So this would give me all the tuples of parent relationships in the database. Bob and I get multiple times, and then Tom, Bob. Yeah, actually, that's interesting. The sub expression came out as well. Pam and parent Bob. Yeah, this Y is also allowed to be a sub expression. Yeah, that's true. And of course, I could have done something else. I could have asked the database for, yeah, give me something where this is parent, and then what does that say when X is Pam, right? Parent, and then here, well, sure, something like that. Yeah, that should return 1 times Pam. So you can go into the sub expressions in this way, and then of course it could have been something like $y, and here I say $y, and now that's nothing. Oh, I say ampersand instead of dollar. And then I I delete this, and then I say I get something like that. Pam and Pat, because this is the pattern that it matches against. So you sort of program with sort of these sub patterns a little bit or something like that. I wonder, is there something like that as well to match the rest of a list or something? That's probably the case. Let's see. The output should contain the following pairs. The order can be different due to Metta's nondeterminism. This is all the parent relationships. Pat, actually. The hell? Was there Pat? There's Pat. So, okay. You add the query in the above program to retrieve only parents and children with same names. Oh yeah, that's cute. Okay, so I'm gonna put this pad. Oh, okay, I'm just gonna type it once. Parent pad. Yeah, so the other query that would be that you say $x, and then I return, well, the pair again, $x, like that. That, for example, I think that would be an example that returns pad. Okay, next page. Functions and unification. Okay. Now we unify. We unify. So yeah. Or this is kind of a relational programming concept, I think, that you have. Yeah, okay. I guess now it goes together. Now that we have these matches and we also learned about functions. Now we put these two things together a little bit, and then let's see. As discussed in the tutorial, evaluable expressions can contain variables, and they are pattern matched against left hand side of equalities. In fact, evaluation of expressions can be understood as recursively constructing queries for equalities. This is kind of the same thing. So we had these expressions that we evaluated, and now we are making queries. It's the same thing, I think, with this match. Consider this code as an example. Okay, I'm gonna type this. Equal only a input a is accepted. Okay, this was this basic equality where this symbol, this expression is allowed to be evaluated to input a is accepted. Okay, then we evaluate only a, and that is something, that is this, that is the right hand side of this. Now only a b is nothing. Well, it's the same. It doesn't reduce further. So this reduced further or was queried further something. Now this doesn't reduce further, and then only a $x that says anything, and it becomes a. Because it basically says, give me, isn't this the same? So they say this here, yeah. Yeah. Okay, now let's bring this together here. That if I evaluate only a, this is the same as if I would say match $self. Equal. Only a dollar result. Okay. Okay, now I understand the relationship. Because we were used to saying this equal sign everywhere, and then it was useful. It's sort of matched to things. But this equal sign is still sort of special because it kind of like makes an automatic match. Now I understand. After looking at match, I understand what this means now. That basically we have this pattern we have this expression in the atom space. So this is in the atom space. So this says, and this is this pattern, or this expression, I should say. So that says equal, and then left side, right side. And here it says equal, I guess. No, not color, whatever. Yeah, here says equal. Equal the left side and the right side. But now I do the exact same thing. So as if this equal is now a parent in the above example. It's kind of like this could be anything. For example, parent. This could also be parent. And then you see that if this is, for example, parent, then matching here, basically with this left side, yeah, it will return basically the right side, because we say give me all the things where the left side is exactly this, and then I return that to you. So I return this here, and that was basically this pattern I passed into match. So now I have yeah, basically this equal sign is kind of like related to this match function via sort of this logic here that I'm guessing this is basically automatic. So when I say evaluate only A, it actually runs kind of this. So it asks what is equal to only A and then the result. So yeah, it's basically querying the database for matches of this, and then we also understand why this here, why this returns, why this ends up returning input A is accepted, because now we basically have this catch-all variable. So yeah, then just with the parent example, this basically finds this equality and basically assigns A to X. We don't use X, we just say result in this case. So we just get this input A is accepted, because that's how we define this equality up here. But yeah, you could I don't know, you could say the var was X, something silly, I don't know. The result was result, right? Then we would get the var was X. So it's like showcasing the case that this X was actually sort of allocated once. So we did say that X is A in the course of this computation, piece of computation, I guess. Okay. Yeah, so this is the flavor of this video. this is me figuring out the language on video. Okay. Evaluation of only A can be thought of as executing this query. Okay, result will be bound to the right-hand side of the function case body. If the left-hand side matches with the expression under evaluation, does it work for only B and only AX? So yeah, for only B, it doesn't work, because there's no, if you look at all the equality patterns in the database, then there is nothing where it says only B here. So you could say only B result, and say result here again. This would just be, this should be nothing, right? Yeah, just like we saw with the parent, if I ask for something that is not in the database. Yeah, and the other one we already saw with this kind of example here, then it becomes A. So that works Interesting. Let us check the following program. Let us check that the following program produces the same result. Okay, I already have this in the atom space. Only input A is accepted. This with equal, so this is kind of like a pattern, but it's sort of a special pattern with this equal sign. But yeah, conceptually it's basically the same. Okay, so now match ampersand self equal only a result. Yeah, okay. This will say only a or input A is accepted. Yeah. Because it simply matches this one thing and then it finds this one. Yeah. Then here, okay, that is the one I already did this. That is nothing, and if you say x, then x is bound to A, and that's the way that this match basically produces an output. So these are the three cases. There's one difference. Okay, match produces the empty result in the second case. While the interpreter keeps this expression unreduced. Oh yeah, that's true. Yeah, I remember. Yeah, that's true. If I evaluate, yeah, okay. Yeah, if I evaluate this, then it becomes unreduced. Okay, so there's a difference between match and the interpreter. All right. The interpreter says, I don't reduce this further, and the match thing would say no result. Okay. The interpreter is performing some additional processing on top of such equality queries, like returning an expression, while allowing the meta interpreter to construct equality queries automatically for evaluating expressions like only A is very convenient for functional programming. While allowing the meta interpreter to construct equality queries automatically for evaluating expressions like only A is very convenient for functional programming. Using match directly allows for more compact knowledge representation and efficient queries glued together in a custom way. Alright, give it to me. It should also be noted that obtaining multiple queries in queries to knowledge bases is very typical. And since the semantics of evaluating expressions in meta is natively related to such queries, the semantics of evaluating, this is what we just saw, that evaluating expressions in meta is related to queries with match. All evaluations in meta are secretly or explicitly non-deterministic. Okay. They're all non-deterministic because match always returns the list of results. So because everything is kind of like match, everything is non-deterministic because it always looks at the list of results. That's roughly how I understand this right now. Okay, I'm gonna put this in. I think I already have these relationships. Let's see. Okay, so now, oh wait, I'm gonna type this to get the practice. Get parent entries $x, $y. Okay, this is now an equality. And now I say match, okay, with the current atom space, then parent $x, $y. So this is all the child-parent relationships, so all the parent-child pairs. Then I return, okay, this is lame basically. $x, $y. That's, couldn't I just say this? Okay, but this list, this is for sure. This is a list of all the parent entries. That is, if I evaluate, so x, y. Okay, let's keep going. What they do. Say another equality, get parents $x. So from one guy, give me the parents. That would be match dollar self, then this relationship. Now I say y, y and dollar $x, and then I return y. So these are all the parents of x. Now evaluate get parent entries. Get parent entries. Tom, and with a throwaway variable. Tom Bob. I get Tom Bob multiple times, and then Tom Liz. And now I say get parents Bob. Yeah, that would be Tom and Liz now. Oh, Pam. What the hell? Also Tom is the parent of Liz, I see. And Pam was also the parent of Bob somewhere, yeah, here. Yeah, so now we have basically expressed this relationship, and we used equalities in order to make this work. So it feels a little bit like writing functions, even though it's all these equalities somehow. Yeah, I mean, the next thing is that we have multiple matches and multiple functions that we mix these two things, I suppose. We can call match from an ordinary function, and we can still pass variable arguments to it. So get parent entries, Tom, and throwaway variable. This works. So x is Tom now, and then y is anything, and this just gives us everything where Tom is the parent. Yeah, and we turn here to we become here x, y, so we get all these children. Yeah. Is equivalent to match parent Tom by, yeah, that's true, because you can basically, well, you can simply pretend to be the evaluator, and you substitute those, and then you come to this. Okay, so these can be mixed. The functions and the variables, they all work together with this match. The result parent, this is the result of the parent list, parent relationship list, where Tom is the parent, is not reduced further. It is convenient when we want to represent pieces of knowledge and process them. The match result is never reduced further, I suppose. Again, parent Bob returns, this result list. Executing match from functions allows creating convenient functional abstractions while still working with declarative knowledge. So I'm allowed to give a name to this function, kind of. I could have said match to express the same thing, but I can also give it a name, sort of as a rule. So I can make functional abstractions, yeah. For example, how would you write a function which returns grandparents of a given person? Okay, let's make this as an exercise. Get parents $x match ampersand self parent y, and then x, that is y. Yeah, that's true. This function is get parents. I already have this. Yeah, I already have this function. Then get grandparents. I mean, yeah, now the cool thing is that we basically use this function twice or something like that. Get the grandparents of x. I have a feeling that I just need to say get parents. yeah, you also you kind of see how this sort of like is a tree that goes up, because get parents of x might be multiple, and then get get parents of the result of that, yeah, is multiple again, perhaps, or not, or nothing, basically. Um, so okay, that's the function. This is the function. This is get parents x. I mean, this is supernatural to express it in this way. I have to say that is yeah, it's quite interesting. Do I get something out of that? Pat. Pat was his own parent. That's why that's really funny. They have this. Okay, one sec. What I'm gonna do is I'm gonna kill the inferior meta process that I have running here. Okay, kill that. And now I run meta again. Okay, so now I have a fresh meta evaluator. And then I'm gonna run this example with the example. This doesn't. Okay, I'm gonna copy with here. Okay, so I'm gonna run this example with the example database. So get parents, get grandparents, and then get grandparents of Pat, Pam, and Tom. Let's quickly check if this is true. So Pat comes up here. So Pap has a parent that is called Bob, and Bob has yeah. So you see that Bob has two grandparents. Well, Bob has two parents, Tom and Pam, and so yeah, basically we went from get the parents of Pat. We found only Bob, and then we kind of did it a second time, and we found all the parents of Tom, all the parents of Bob. Sorry, and we got Tom and Pam. This is fucking amazing. Yeah, this is quite cool. Um, so the thing that is truly fascinating about this is that the function get grandparents is expressed in terms of get parents x, get parents of the result of that. It's just I like the alignment between my mental model of what a grandparent is and the function expression here is so close. Um, it's yeah, it's impressive. I don't know. It's impressive. Um, I just say it's impressive. Um, you also you can just write code, and what you thought would make sense is just the thing that makes sense. So it's yeah, there's something about that, that's for sure. You can't dismiss this. This is interesting. Okay. Okay, so after the grandparents example here, from facts to rules, one may notice that equality queries for functions suppose that there are three variables, not only in the query but also in the atom space entries. Queries for functions. So yes, exactly. Yeah, we were typing all the time. We were typing something like this function here, and there you have a free variable, for example. So that was already the case that we were programming with free variables in the functions that we made. These were these expressions that we put into the atom space. They can also have free variables. We already did this with the functions. These entries can be not only function definitions, but other arbitrary expressions which can be used to represent general knowledge or rules. Okay, so here is the example where we have a little database, parent Tom Bob. This here. Twice, now I have it twice. And parent Bob Ann. Then we have something like, instead of an equality, now we say this implies relationship between two sort of sub-relationships, I suppose. And now it becomes a little bit wild. So deduce is a function that matches, and it basically looks for these implies things. And then afterwards, it queries the database with the outcome of the implication. I guess that's called the implication. I would think that the right hand side is called the implication. I'm gonna ask Claude maybe. In logic, what is an implication? Is this a good question to ask? Logical consequence. This is a logical consequence. Oh, it's called consequence, not implication, I guess. That, for example, an implication often written as P arrow Q, if P then Q, is a logical relationship where the antecedent P is true, then the consequent Q must also be true. The implication is only false when P is true and Q is false. If it rains, then the ground is wet, Q. Sure. The logical consequence, also entailment, is a fundamental concept in logic. It's kind of funny. The original contribution to the relational programming code base are like the early logic people. I guess that's the early Greek philosophers or something. I find this kind of a funny thing to say. We say that something logically follows from some statement. That's a logical consequence. Okay, so I'm guessing that this here is the antecedent and this here is the consequence. Okay, so I guess now I get my implication is the name that I gave to the thing that is actually called consequence. Okay, good to know, I guess. So we take the consequence and then we return sort of the match of the consequence. So basically deduce returns filled in consequence. And I also tried deduce 2. So if I say deduce, I get child Bob Tom. There was, yeah, it's kind of similar as asking the database for all parent relationship things, but yeah, now the cool thing is that we program with these logical implications here right now, because we are allowed to say child, and then that's filled in, and this is basically instead of writing a function, we wrote this pattern. Yeah, and this deduce 2 here, that would be something else. That would just return the pattern B. So that would still be this pattern B. That's why we had this match. And conclude is the flipped version where you say parent Bob and then you get the child, the filled in child things, all of that. I didn't evaluate conclude yet, I think. Yeah, child and Bob. Okay. Yeah, now the relationship between this and the frog example. In the frog example, that would have been, I think, we would say parent Tom Bob true. I think this was with capital letter. and parent Bob and true, and then we would have been able to say that we would have been able to define equality called child dollar x dollar y, I suppose, would be parent dollar y dollar x, must be flipped, right? That would return true, but yeah, maybe you do this, something like that. That would basically be this frog, like that. That would be the green thing. This so now you could say if child dollar x dollar y, then say that dollar x is the child of dollar y. But yeah, like the deep relationships and so forth between these things, I'm still exploring here. Incorrect number of arguments. I have this different here. Either, yeah, change the error child. Incorrect number of arguments. Wait. Ach, the if statement has an I think, yeah, like this. Also incorrect number of arguments if parent. So true. If child, like this. No, incorrect number of arguments. What happens if I evaluate this? This should query all the child having relationships. Yeah, so there's 2 child having relationships. Then I could say yeah, I mean this already does it, right? Is the child of, and then I would say Bob is the child of Anne is Anne is the child of Bob. Bob is the child of Tom. Yeah. So this would also be true. At least I have reproduced something a little bit that that is, I think, roughly the way that you would say it in terms of these Boolean values. But yeah, I have to admit my ignorance. This is still very strange, very strange, very strange concepts. So that this thing is a rule. Okay, I get this. That this is a fact. This is a rule. Yeah, and I also sort of see that you can program in this way, but like now, basically deciding between these 2 ways of doing it, I would right now have not really an idea, but that's why I'm getting into it. And yeah, I mean, you get into it, then you write some code, you look at what other people have written, then you update your style to be a little bit more like what other people have written, and you go back and forth with your style and reading other people's code, and eventually you write code and it looks like and looks like what somebody else would also write, and you go like, oh, actually I know what. But yeah, okay. So now I have seen this kind of logic. Okay, this is that we can represent general knowledge or rules. Yeah, okay. So this for sure is quite cool. That there's almost nothing that actually talks about parents and childs, except for this line. The rest is sort of general, I guess, helpers for this deduce and this conclude function. So very, very general. And this is general database knowledge stuff. So really, there's kind of like only one line that talks about parents and children and gives us this power here. So it's for sure interesting. If child and parent were predicates returning true or false, as in the frog example, we could somehow use equal instead of implies. I have child, parent. Yeah, parent returns true if the two parents, for example. But we could also return false. Naja, I just continue in the text with German accent, probably. We could somehow use the equal instead of implies. But here we don't evaluate the premise to true or false, but check that it is in the knowledge base via the match operator. It makes inference better controllable. We can easily go from premises to conclusions with concludes, or to verify conclusions by searching for suitable premises with deduce. Yeah, so this implies is doing some work where basically we relate a left and a right logical relationship, a precedent and a consequence. So I mean, one feature of this kind of programming that also that you notice is the way that left and right are completely interchangeable. That is, you literally just flip left and right here once. Between conclude and deduce, I didn't even flip so much. I just say different variables given coming from the outside. You don't even flip anything. It's kind of funny. So left and right are completely on the same logical level, at least at first glance. So completely different from sort of procedural programming where left would be the function name and right would be the function body or something. It's like it's just two completely different things. We will discuss different ways of introducing reasoning in Metta in more detail later. What we want to focus on now is that both cases are in both cases a query with a variable is constructed. Say implies parent Bob y, and then b. That would give all the this would give all the consequences, or it would put all consequences into b. Yeah, something like that. Yeah. Where the antecedent was parent Bob y. And it should be matched against some entry in the knowledge base with variables as well. Yes, exactly. This is an entry in the knowledge base where there are variables set. That's how we can program something more general, I suppose. That would be a way of introducing reasoning into Metta. Yeah, okay, reasoning in Metta, you usually have you have some kind of entries in the knowledge base where some things are variables. Okay, I get that much. In our example, the operation is called unification. So in our and this operation is called unification, and it is available in Meta in addition to match. Okay. So unification is now another thing. All right. Let's talk about unification. The function unify accepts two patterns to be unified, matched together in such a way that the shared variables in them get most general non-contradictory substitutions. So it's kind of like the least common, the largest common thing that still makes sense, or something like that. Like some kind of shared subset or something of possible solutions, I think, and it's the largest of these subsets or something like that. That's how it sounds to me. So I think this is called conjunction as well. I'm guessing that there's a relationship between unification and conjunction. Conjunction or unification and conjunction are distinct concepts. Conjunction, this is the logical operator that combines two or more propositions. For example, A and B, then both must be true. Unification, on the other hand, is a process of finding substitutions that make two logical expressions identical. When we have multiple conjunctive goals, P, Q, R, unification is used to solve each goal. The unification process helps satisfy the conjunctive constraints by finding consistent variable bindings. Alright. Okay, I'm gonna type what they say. Or I'm gonna read what they say first, and then I'm gonna type what they say. The function is evaluated to its third argument if unification is successful. Okay. So unify takes 4 arguments. All right. And this can also fail. This can succeed or fail. It's also interesting. And the fourth, if otherwise. The following program shows the basic example. Okay, so I call a function called unify. Now parent x Bob. I'm not sure if that. I have something like this in the database called that returns true. Will this work? Tom $y is also true. The output for successful unification. Okay, so basically if I find a subset of variables where both of these end up being true, suppose, then I'm gonna go into this branch and return this branch, and else something else. So I actually get Tom and Bob. I guess that's because I had here Tom and Bob actually as patterns that are able to be filled in here. So I said that Tom, Bob, that this pair would be a parent. If I say Tom, Bob, that was true. Yeah, I could have also done basically something very similar with this match. xy. What does this do? That would be all the parent relationships. Bob and true, Tom, Bob, true. Yeah. So I think here's something else, because there's a second one where Bob is the child, right? I have a second one where Bob is. Oh no, I have Bob as parent here. Bob is parent of Anne, and then but if I would make Bob also a child of somebody else, like Alice. Oh wait, I need to say this is equal to true. In this case, now I would get Bob as child twice. And then if I unify a parent, so here I still get Tom and Bob for this unify, but if I would say here this is dollar anything or something, yeah, now I should, oh, I get dollar X Bob. Oh. So it does unify it, but basically says that I'm not gonna put anything into X. So because I don't use X here. No. Ha! I'm surprised. Yeah, interesting. It's kind of, it's really nice if when you make an experiment and then it's something else, like something that you didn't expect. I love that. What the hell? I say, why is XY? So that unifies with parent XY. Parent Tom Bob unifies with parent XY, where this is just Tom Bob. Okay. Why do I think that my parent equalities here even have anything to do with this? If I say here parent 2, this still also unifies these two things. Yeah. Yeah. That's really funny. You say here X, you still get Tom and Bob now. Yeah, because you see that there are values for X and Y where this unifies. Okay, I kind of see that logic now. Now, if I say, yeah, you can put anything here, Tom Fu, right? That would also be Tom Fu for X. How can you even make it fail? By saying something like this. Yeah, now the pattern doesn't match. Yeah, okay. And but even this would also match. Yeah, because Y is a catch-all kind of thing. What can I say? Dollar Y. What happens if I do? This fails. When here B, when it says here B, now I get, of course, Tom Fu and dollar Y is A, right? And then it unifies like that. If this says something else, then it fails again. Okay. So I don't even know if this doesn't do anything with the knowledge base, or yeah, I guess it doesn't. Yeah, you would need to match here, for example, and now you could do things. Not entirely sure. Yeah. Or do I need to say evaluate? No, this is the. What is this? What would this be? Parents. Isn't this like, and this is 3 times just true or something? This just fails, right? As an error. Unify. Incorrect. That's interesting. Incorrect number of arguments. Set the error. Incorrect number of arguments. Error in unify. Huh. Yeah, okay, but I'm on video playing around with this language. Okay, so now I played around with this. I played around with this to some extent. I still don't. If I say match, well, let's say match $self and then something that always matches, and then say something like, what does this do? Oh, it says true a bunch. Funny. And something like this, does this so this says true, so because I'm evaluating that one here now, I guess. Okay, what if I say parent 2? That's not in a database. Okay, that returns parent 2 a bunch. So this returns for every atom in the database. It returns this outcome. I understand. I think that's what it does, and I think that's what it does. If I put a catch-all variable here, just query all the atoms, all the expressions in the database. I think. Okay, and if I do something that doesn't match at all, then I get nothing. Yeah, okay. I need something. Yeah. Okay, let's quickly pretend that there's something like foo bar in the database. Okay. If I say foo bar, I get it once, right? Yeah. So this is completely random. I just get something because I want to understand what happens if I put this here. Error, grounding space top. What does this say? Incorrect number of arguments. Huh. Okay, I don't understand it. Here like this just failed. So because now I'm passing in this match, expression as to unify or something, and that just doesn't make any sense. That would make sense if I had another one here, and that would. What does this do? Overflow the stack. Man, I'm breaking it. What if I copy the example again? I say here $X and Bob, and here I say Tom and $Y, and now I have some stuff. Oh, it just died. So inferior meta. It died from this. Oh, it returns what? What? It returns why did now return 225 times Tom and Bob is something that I don't understand yet. I thought that this whole match blah blah stuff would not matter. That it was basically would be but I can try that as well. So if let's say that I pass something wrong here, I just get Tom and Bob. So I think it's just treating this as an expression, and in this version, this really does something. Does the match really do something in this version or not? It seems to do something because I get way more outcomes for some reason, for reasons that I don't understand yet. Okay, I'm gonna type in this unify example here again. So parent $X Bob, parent Tom $Y. So you kind of see how these are kind of compatible, right? And then I return the tuple $X $Y, and else fail. So you see that this comes out. Yeah, and I have, if I put something like this here, it fails. Okay, so these patterns have to match. Well, I guess they have to unify or something. There needs to be a subset of variables that fit. Here we unify two expressions. That is parent x Bob and parent Tom y. And return a tuple $x $y. If unification succeeded, the fail atom will be returned if there are no matches. Note that unify, I'm gonna copy what they say. Note that unify, that is some variable, and then that is the other variable, yes, no. That will come out to no, because $x should have the same binding in both patterns. So yeah, then yeah, it can't decide. X can't decide whether it's B or A. So this doesn't result in a unification, I guess. It cannot be A and B simultaneously. One of the first two arguments can be a reference to a space as well. Oh, that's what happened to me. Oh. Okay, so parent Tom Bob. Let's type this in. Parent Bob N. Okay. Then unify. Now I say $self. So the first argument is the space. Okay. So take the space to unify parent $x Bob. Then return $x else, return fail. Okay, this will come out to Tom. So a space that basically allows it to be yeah, like many patterns, I think, instead of just a single pattern. I guess that's kind of the trick with the space. This will work like match, but with an alternative option in the case of failed matching. Achso, okay. That is the same as match. Okay, so unify is, if I understand correctly, unify is a little bit like one level below match. So match really means that you take a space and unify it with a pattern, I guess, and then you return the outcome. Well, yeah, you return the outcome, yes, with the filled-in things, yeah. And the unify is more general, where you can put two patterns, and then it's also unrelated to the space, I think, because here I have parent, blah blah blah. This actually returns to $x. Yeah, okay. So it's actually saying that X can be anything still, kind of like it's like this is actually a subset in the unification where there's one variable that is still allowed to be anything. I think this is kind of what happens if I say something else there. Yeah, that also is this, yeah. And if I say Tom here or something, yeah, then that's still this one variable that's allowed to be anything. And now it's Tom. But this doesn't have anything to do with the space. But I can put this space here too with ampersand self. Yeah, in this case I get Tom right now. I could swap this. If I swap this, I should get Anne. Yeah. And this is basically the mechanic that match is using, I suppose, with an optional fail as well. Okay. Here we pass a reference to the current space as the first argument. So the second expression, parent $x Bob, is matched against the whole set of declared knowledge. Yeah. All right. Next section. Chains unification. Let us analyze how conclude parent Bob $y from the above example is evaluated. That was this conclude. This was quite complicated. So here is this conclude parent Bob. Yeah, this is this part. Yeah. Okay, so at first we go to here. We say that match self parent Bob result is executed. Yeah. So basically I can play evaluator for a moment and put this in. So that's true. It says match, and then here we go to one sec. Why is that is equal here? One sec. From the above example. Wait, where's the conclude example? This one was the one with the implies. Then the unification, and here chain unification, conclude parent Bob. Why is there this? Because here I have this implies result. Conclude parent. So yeah, they come here to this implies. Yeah, okay. Okay. So they are fully with me here. All right. Okay. So you are looking at. I thought conclude is. I thought this is expanded basically to this part, but it's not. Wait, it's first also calling. It's first calling match self. Then it looks for the equalities. $y results. This happens. I didn't. So this happens. So now I get it. Okay, now I get it. Okay. Because of the evaluation model, obviously, we have this as a function basically, and this is the arguments. So in our evaluation model, we first go through all the arguments and evaluate them. And evaluating means that you match against the current atom space. So it's equivalent to this. So eval the arg. There's only one arg. So as a sub process, it evals to this expression. So we look for the equalities in the current atom space in order to evaluate the args, right? And this is basically the same as using match to say there's an equality, there are pieces of knowledge where there's an equality sign, where the left side is this, what I'm saying, and the right side is some result, and then I return a result. But this just returns nothing, okay? So the evaluator now try to eval this, try to look, or try to match in atom space or something, or match this, execute match, sort of look for equal sign expressions in knowledge. Okay, now this returns nothing. or the empty result list. I'm not entirely sure. So it's the outcome of this sub part, but this query returns no result because equalities for parent are not defined. Thus, parent bob y remains unreduced. Okay, so because there's no result, it remains unreduced. So parent bob y is unreduced. But they could have reduced it. That's kind of important as well. So if you put something here that does reduce to something, it is a way to compose. It's a way to compose abstractions in a language where this would be another subroutine or something. So that we're able to nest expression evaluation trees. Something. I'm just trying to say something somewhat coherent. But yeah, I guess you get what I mean with we can compose. I'm not sure. But this returns nothing. Thus, this remains unreduced. Okay. Thus, the equality query for the whole expression. Yeah. Okay. So then this whole thing is. Aha. Okay. So it takes the whole expression and says this. Okay. With this not substituted in, basically with this being completely there, this expression being completely there, and this of course returns something now because we did make equality up here that has conclude anything on the left side, and on the right side it has this match expression. So if I evaluate this, then result will be substituted to this match expression. Oh, nothing. One sec. Maybe I didn't have this. Maybe I didn't evaluate these. Yeah. Okay. So and then okay. So at first, it comes out to this part. The result is done already. That the end result is that, yeah. The follow. Okay, so we execute this. We basically look for the qualities using this as input. We look for where are the right hand side things of equal signs. That would be this. The following two expressions. One is the query, and the other one is from the space are unifiable. Oh. They are unifiable. Ah, yeah. So conclude a, yeah, this one is from the space, and this one is from the input, or from the query. Okay, from the query. And these two are unifiable. And actually, I could call unify on this expression. Can I? And then return the result as fail, I suppose. match. Okay, I guess this makes sense. And this is how the result looks. I guess this is how the space prints when you print it out. So the result in this case is, well, this part, right? Match, and then with stuff filled in, because we need now say that $A is filled in. Yes, $A needs to be filled in to a certain degree. So it is this. It is just this. It's literally just this. $A is this part. So the result of the unify here is that that here $A is this part. This goes here. Yeah, so then I have match space implies then this A is filled in. That comes from the query, and then match space. Match space. Then the query again. This is also the A again. So it also went here, and then it came out here. And B stays. B just stays. Okay, so $A is bound to parent Bob Y, yeah, and result will be this part. Result is kind of this part. Yeah, is this part where this is. Yeah, I'm gonna copy this again as well. So $result, that's the same thing except that the space has a different name here. Ampersand self. Yeah, and one thing that is cool about this, I can just evaluate this, right? Oh, this overflows. What? Actually, my meta REPL is also dead now. Core dumped. It's kind of funny. I'm gonna evaluate all these things again. That is an overflow? Oh, maybe because I accidentally. No. Okay, I don't know why. It's for some reason. Obviously for some reason that I would at some point understand, but not right now. It's not important right now. So yeah, so it, we now expanded it to this part here. Yeah, and the important thing was that there was in between basically this unification, so you kind of know the mechanism of how the evaluator works. This is quite variable to work through it like this. Okay, they have more here, I guess. Okay, so here we are now. This is the result. Yeah, it's this part. Now match is executed directly as a grounded function. Okay, this is the next thing the evaluator is doing, because now it looks at this expression. It can say, I'm gonna evaluate this expression, but match is a grounded function, so match is doing something now. Otherwise, another equality query would be constructed. So, okay. Just because match is grounded, it's going off into the match. Otherwise, yeah, it would now do more more equality query on the space, the way that it already did with this conclude part. It also already did it with this parent part, but the parent part didn't have any result. That was the first thing that it did. Yeah, it tried to reduce this didn't work, then it reduced the complete thing, and that worked, and that resulted in this match, expression. This implies parent Bob y b as a query. Yeah. It would try to match with this as query, but it doesn't, because match is a grounded function. It unifies with the following entry in the space. Yeah, so the match operation unifies now. So we could also type this. Unify implies parent Bob $y. So this part, yeah. And then there was this other thing, child. First of all, this is $b. This is our query. Yes. And the space also has something to say. This child dollar. I can also call a unify function like this, and basically, and then like this or something. Implies parent child. Oh, funny. That says $y number something. I'm not entirely sure how this came out. And these are two different. Are these two different y's? So these are two different y's. That's why I needed to put a gensum kind of thing there. Okay, one may notice that there could be some collisions of variable names, and the interpreter should deal with this. In overall, $x gets bound to Bob, and $b gets bound to child y Bob. Since the output of this match is match $self parent Bob y b, yeah, the expression for further evaluation becomes since the output of this match, wait one sec. Well, yeah, okay. Well, we are here implies parent Bob this. Yeah, this is where we are here. I can also evaluate this piece, and I get something with. Oh, I get $b. So yeah. If I would say here implies something like that, then I would get child y Bob. But yeah, let's not. The expression for further evaluation becomes one sec. So we are here. We say match everything with implies. Then we unify it basically with the space. Yeah, we get this basically. Yeah, we get this. Yes. So there comes out comes this This is we're basically still looking at this part, I think. Here. So yeah, then we find in the space, we find something like this. Only that there are variable name clashes. Oops. Let me. But why the variable name clashes? It somehow deals with this, and it somehow comes out to this. Because this is important now that this actually is the same variable. How that actually works, this kind of went past me now a little bit. They say here, and the interpreter should deal with this. There can be collisions of variable names. But this was exactly what we wanted, wasn't it? Oh, yeah. Okay. No. No, okay. No, okay. So we are still expanding kind of this part of the match pattern here, and now we have expanded this part, and we are still expanding. Now we call match after we. I guess you keep calling match or something like that. We came out to this part. Then match is executed as a grounded function. Okay, so match is looking for a match with this part. Yeah, we're still looking for a match with this part. That unifies with this thing in the atom space. In overall, $X gets bound to Bob, and $B gets bound to child Y Bob, so something like this. Since the output of this match is okay, now we're here. Okay, now we're here. To the output of the match. Okay, because of this. Okay, so here this is to the output of the match filled in, I suppose. With this $B filled in, this child $B filled in now, yeah. That means that $B is filled in with child $Y Bob, like this. So that is this line. It expanded now to this part, and it says ampersand self here. Okay, so this is the expression that the evaluator is looking at right now. And now it makes a unification again. So this basically goes off and says unify. The pattern is this part. One sec. was not correct. I was not correct. It's this. It's this. There was no implies here. That was only used in the unification step, kind of. Okay. I should have maybe to make it more clear, maybe I should have returned B here. Yeah, that would maybe look a little bit more clear. Because B is the thing that is substituted here. And okay, so this part goes on to unify, where we say parents as query. Yes, we say parent as query. And basically the second part of the query is the atom space again. And then the outcome, I think, yeah, this would make sense. The outcome is this and else fail or something. And then you evaluate this, and this actually says child Bob. And so now we are at the bottom. Yielding child Bob and okay, so now it keeps on going, and it asks for the equalities again. So actually, I think it kind of asks for this, where there's the pattern, where this would be the left side, and then the right side would be anything. And because this doesn't return any results, it stays with this outcome. So this is then the final outcome now. Right? Yeah. Okay. There's no matches, and then it's the final result. Yeah, okay, here they have written it down. The overall chain of transformations in the course of interpretation can be viewed as conclude parent Bob Y. Yeah, first it would also look for this, but then yeah, this didn't reduce further. There were no equalities. It tried to match, but there were no equalities. Okay, then it matched for this, and it found this. Basically, this is sort of like, yeah, it found this equality that we had. That was the conclude equality up here, this part. So basically it puts that the right side of this equality with the things filled in order to do that, it was basically in effect doing a unify. Now this one, this is this part, basically unifies with the space again to kind of find this B. And then we happen to return another match expression. So this is number 3 here now. So that B is filled in now with this child consequence. So this is this line. Then we unify with the space again, and this time this is the query, and yeah, this is the space, the query, and the space, and in the result we fill in this. Is this? Yeah, I guess this makes sense. Yeah, yeah. It looks so simple, but at the bottom it needs to be something simple. Yeah, at the bottom we just ask, like this one just asks the space, who is parent, like who is in this Bob parent relationship at the second spot? Why, like who is the child of Bob? Like that must be the last question to answer, to ask. Kind of makes sense. That the last question to ask is something very, very simple. Just ask the space, is there any child of Bob? Basically, that's what it reduced to And the answer was that yes, there is a unification basically where y is n. So I can put in with the knowledge database, I can find a y that unifies with what you're saying, so that y is n, and then I return to you this form where y is substituted in, and that's child n Bob. And then I look at this child n Bob and I try to reduce it further, but it doesn't reduce further because it's kind of bottomed out. There's no other equalities. Yeah, so basically you can kind of break it, or I don't know, like you can do something strange. Like if I'm up here in my database, right, and I say child and Bob, I don't know why, but if I say that this is foo, I don't know, for some reason I say that this fact is foo, equal to foo. If I now conclude again, I get foo. And I don't know, this must be some kind of challenge to this whole paradigm. I mean, it's kind of like, but wait, this is, shouldn't I get like, I don't know, shouldn't I get this child thing, like Anne and Bob, like wasn't this so important? Maybe Anne and Bob was more important than Foo, and somebody's like after the fact basically making another equality into the knowledge base and says that yeah, this means Foo. So now everybody that is querying the database gets sort of the final result, like the last answer. This must be a problem to this paradigm. The last answer problem. I don't know. Maybe they have an answer to this. Maybe you can say, oh yeah, maybe you can say, wait, you can say stop. Um, hmm. Here I say conclude a. I wonder, can I say, wait, but I want you to stop at child something? I can. Wait one sec. I can instead evaluate. I want something, but this is also. I mean, yeah. Wait. I mean that sounds like a downside or something like that. I wait, but I can say I want something. Child. Uh. Hmm. Why, Bob? I mean, this would work. I think. Now I just say. Ah, this still says child and Bob Foo. Oh, it says Foo Foo. Ach so, it says Foo Foo. And then doesn't sound like what you want. This Foo is cluttering the database. Okay. Wait one sec. I'm gonna try to do it with match. Okay, so match the database. I wanted to say conclude. I can't. Oh, wait. I can say match conclude parent, but this will just say foo, right? This will say match foo. If I say result, this will say foo again, right? No, nothing. Okay. I thought it would. Can I say an exclamation mark here? No, this is an error. Incorrect number of arguments. Okay. Um. Hmm. Okay, so I mean, I could of course say this. Well, this is boring, right? Yeah, this is boring. Yeah. Dollar $X. Yeah, and then return me this relationship or something. That should say an again. Oh, this also comes to foo. Ah, yeah, true. Yeah, yeah, true. Because it looks at child Bob Ann again here, and evaluates, reduces it further to foo again. These are not okay. Continue in the text. These are not all the steps done by the interpreter, but they give the overall picture of what is really going on under the hood. Next page.